Mars continues. The perseverance of humanity launching the next generation of robotic explorers to the Red Planet.
NASA's Mars Perseverance rover left Earth 6 months ago. Now we are preparing for touchdown on the Red Planet tomorrow. The rover will attempt to land in Jezero Crater, which is the most difficult landing site on Mars ever attempted. But the Perseverance rover and the team are ready. Welcome to NASA's Jet Propulsion Laboratory in Southern California. I'm Marina Jurica, your host today, as we bring you a mission landing update as the team continues to prepare for tomorrow and what lies ahead. On our panel today are NASA Planetary Science Division Director Lori Glaze, Perseverance Deputy Project Manager Matt Wallace, Entry, Descent, and Landing Phase Lead Al Chen, Deputy Chief Engineer for Medley 2 Caitlin Lyles, Deputy Project Manager for Surface Activities Jennifer Trosper, Perseverance Project Scientist Ken Farley. For anyone watching who would like to submit a question, you can do so by using the Countdown to Mars hashtag. Our phone lines are now open to the media. You can ask a question by pressing *1 and enter the queue. To start, I'd like to welcome Lori Glaze. Good morning, Lori.
Good morning. Great to see you. Wow, I'm getting so excited. We're now just a little over 26 hours away from touching down on the surface of Mars. And I was just thinking this morning, remembering back to the launch back in July and that exciting moment when Perseverance and Ingenuity began this incredible journey from Earth to Mars. And now we're here just 6 months later, ready for that final leg of the journey to put us on the surface of Mars so that we can really begin the overall objective of this mission, which is to really do the exploration of Jezero Crater. Perseverance is taking our next step in exploration of Mars, especially addressing the question about whether life ever existed elsewhere in the universe. Can I have the first graphic, please? Thank you. In studying Mars, we've taken a methodical approach to better understand how to even look for life. And all of our rovers have played important roles in trying to improve that understanding. Perseverance, of course, is going to be our 5th rover, the first being Sojourner, which launched in 1997. And that methodical approach started really with the Spirit and Opportunity rovers, following the water, trying to understand the history of water on Mars and understanding if there were ever a time when there was enough liquid water present on the surface of Mars to support life. And then that was followed, of course, by Curiosity, where we really took the next step, which to understand the habitable environments, whether there were habitable environments on Mars, and of course, Curiosity being able to confirm the presence of a lake of liquid water on the surface of Mars that was sustained over a period of time, and also identifying the complex organic molecules that would be the building blocks for life. And we've built on all of that knowledge to prepare ourselves now with the Perseverance rover, which is going to take that next step to really actually look for those signs of life. And we've brought with us an incredible payload of instruments that can, of course, do incredible science on the surface and also help us to identify the rocks that we'd like to take samples of and eventually bring back to Earth. And if you can run the video, please. This is just showing the rover as it's drilling down into the surface to collect those samples. We're going to try and bring back a scientifically diverse set of samples. You'll hear more from Ken Farley later about that. And this is just so incredibly important to bring these samples back to Earth because we can then use the full breadth of our capabilities in the laboratories we have here on Earth, using all of the scientific expertise from around the world to address this incredibly hard question about whether or not those fossils of the microbes actually have been preserved in the deposits of Jezero crater. And so with that, I'd like to hand things over to Matt.
Thanks, Lori. I just want to re-emphasize something that Lori mentioned, which this is really a different rover. You saw the profiles of the previous 4 rovers. I had the good fortune to work on all of those, and this one's really at the top of the food chain, I'd have to say. You know, we're carrying almost 50% more science and technology payload than Curiosity, despite the similarities in the 2 vehicles. This is really a much more capable system. And I think not only do we have the transformative science, which Lori and others are going to talk about today, but as mentioned, we have a lot of feed-forward technology on this mission, whether it's the Ingenuity helicopter or the ability to make oxygen from the CO2 atmosphere on Mars. A lot of exciting technology work that will feed into future missions, including some you'll hear about today, the Medley 2 package. Really just a great mission coming up. But before we can get that surface mission going, we have to land safely on Mars, and that is always a challenging feat for us. This is one of the most difficult maneuvers that we do in the space business. You know, almost 50% of the spacecraft that have been sent to the surface of Mars have failed. And so we know we have our work cut out for us tomorrow to get down to the surface safely at Jezero. We're going to ballistically approach that planet at about 12,000 miles an hour. And the trick we have to perform is to slow down to just a couple miles an hour so that we can gently touch the vehicle down on the surface and safely do so. That all has to happen in about 7 minutes. And it all has to happen autonomously. Perseverance really has to fight our way down to the surface on our own. It's something like a controlled disassembly of the spacecraft, and it's always something that we think a lot about, we work hard on, and we prepare for. And once we get down to the surface of Jezero, she won't necessarily find the most welcoming site we've ever been to. Jezero is a fascinating scientific location. It's got great craters, it's got rock fields, it's got sand dunes. All of those things are interesting for the science community, as you can see here in this imagery. But all those things also represent landing hazards for the spacecraft. And so we do have a new hazard avoidance capability we call terrain relative navigation, which we'll employ for the first time. That's really enabling us to go to Jezero when we couldn't before. Jezero is actually a site that was scientifically interesting to many previous missions, and we just couldn't get there until this point when our technology was ready to support it. So all that's coming up. We are currently about 150,000 miles from the planet. We are picking up speed as we approach, and the gravity starts to pull us in. We have transitioned into our EDL mode of operation on the spacecraft with the command we sent last Friday called do EDL, do entry, descent, and landing. We're keeping a close eye on our navigation situation. We have to hit an entry corridor that's really just a handful of kilometers across after traveling hundreds of millions of miles to Mars. And that's always something at this point of the mission that we're keeping a close eye on. We are updating the parameters, so we're ready to land right where we want to in Jezero. Our batteries are now topped off at 100% state of charge. Our pyro systems are armed and ready to execute the deployments necessary to execute entry, descent, and landing. We have tested out our engines and our guidance sensors. They are ready to go. And really just have a few more interactions with the spacecraft, but if necessary, Perseverance could land itself already without any more help from us here on the ground. So the spacecraft is ready. I think the team is also ready. We've been thinking about entry, descent, and landing for probably every workday over the last 8 or 9 years. It's always something that consumes our development and our testing and our design work. We've been practicing the entry, descent, and landing process using something we call operational readiness testing, especially over the last 6 months or so. It's going to be a little bit different this time, obviously. On previous missions, we're going to be having to deal with the same pandemic that everybody else is dealing with here. So our workplace is a little different. We've got masking requirements and social distancing requirements. Our mission support area will be a little less dense than we have before, but make no mistake, this is going to be a landing on Mars, much like the previous that we've had on other missions. And so I think with that, I'm going to turn it over to our entry, descent, and landing phase lead, Al Chen.
Thanks, Matt. Matt just told you a little bit about the spacecraft and team readiness, so why don't I do the traffic and weather as we get closer to Mars here. If you bring up this next image here, you can kind of see our Martian dartboard, if you will, figuratively here. If we're inside that green box is our bullseye. That's where we want to be, and that's anywhere in that area, the entry, descent, and landing system can finish the job of getting us down to Jezero Crater. As you can kind of see from those rainbows of little ellipses there at the top of the box, we are comfortably inside that box right now. So we think that the landing system can finish the job from here. So we have hit that bullseye. That's pretty incredible considering our last maneuver was back in December. If we move on to the weather, I guess we just entered spring in the northern hemisphere, which is actually the beginning of the Martian New Year. So I guess a happy belated New Year, Martian New Year to those of you who celebrate. But the weather conditions look pretty favorable for us right now. As you can see from this image, the conditions are seasonal. There are some clouds that are out there and some polar cap edge storms, but nothing near our Jezero landing site that's over there in the white. The skies look very clear and good for landing tomorrow. But even with clear skies, landing is the most critical and dangerous part of the mission. We just can't guarantee success. So let me walk you through the critical events of EDL, all of which need to happen without any help from us here on Earth. Perseverance will have to do this all on our own. So before we get to the top of the atmosphere, we separate the cruise stage that's helped us all the way through the 6 or 7 months since launch. We'll hit the atmosphere going at about 12,000 miles per hour and use that atmosphere to really slow down. We'll have to survive the intense heating and G's, the deceleration that come with that, but also steer our way to the target as we use thrusters on the back of the vehicle to steer our vehicle all the way toward the target. Once we slow down to supersonic speeds, going about 1,000 miles an hour or so, Perseverance will deploy a large 70-foot diameter parachute while still traveling almost twice the speed of sound. So that'll slow the spacecraft down even further. While still slowing down on that parachute, Perseverance will need to figure out where she is. So she'll separate that heat shield, that's kind of like the lens cap for us, but that heat shield protected us through entry. And it'll get a good look at the ground using the radar system to figure out how high we are and how fast we're going. And then also a new system that we call terrain relative navigation that gives our vehicle eyes and the ability to really see where she's going and figure out where she is. But even when the parachute's done working, done slowing us down, Perseverance will still be going about 160 miles an hour down. And that's too fast to land. So at that point, we'll drop out of the back shell, fire up engines, those engines that are on the descent stage, that's the rocket-powered jetpack that's holding onto the rover, and fly to a nearby safe spot using that terrain relative navigation system to target a nice safe spot. Once we're about 70 feet above the ground, we'll start the sky crane maneuver. And that's where we separate the rover below that rocket-powered jetpack, deploy those wheels of the landing gear, and put her down safely at a little less than 2 miles an hour. Once that's over, the descent stage will fly away to a safe distance. So that's all about how Perseverance is going to land tomorrow. Let's talk a little bit about how we're going to hear about it. So if you pick up the next figure here, there's a couple ways that we'll be able to hear what's going on from Perseverance as it's happening. The first is this direct-to-Earth path. So the vehicle can communicate direct to Earth via something we call tones. Because Perseverance is busy landing, she can't really spend the time to point her antennas toward Earth, and Earth is really far away as well. So these tones are very limited in information. All we have there going direct to Earth is kind of one of 256 tones. They're like keys on a big piano. And sometimes we can use those tones to tell us different things, like the heat shield has come off or something like that. Unfortunately, once we get down to about backshell separation, Earth will set below the horizon for Perseverance, so the tones will end. But that'll take us all the way from kind of before, from cruise stage separation, all the way down to backshell separation or so. Next, we have a second path, that's through the Mars Reconnaissance Orbiter. We've developed a new system a new set of software on the Mars Reconnaissance Orbiter to allow us to relay data as it's coming from the vehicle, so all the way up from Perseverance while she's landing, up through MRO, and then down all the way to Earth. That gives us about 8 kilobits per second of data. That's kind of like half the speed of old school dial-up, if you remember that. But that'll allow us to see a lot of different things, like what the vehicle is doing. If you cue up the next little video here, we'll be able to show you what's going on in real time and show ourselves as well. We'll be able to see what mode we're in, where we think Perseverance is looking, how fast we're going, and how high we are above the ground, even an estimate of how much fuel we have left as well. So we hope to use that to assess what's going on and to show everybody else what's going on as it's happening. There's also another path that we get data from another orbiter that's going overhead, the Maven orbiter, but that data won't be available until several hours after landing. So I just want to be clear that with all these different communications paths to get data back down to Earth about how entry, descent, and landing is happening, none of them are required for landing. Perseverance will try to land herself no matter what, even if we don't get any of that data tomorrow as it's happening or afterward. The vehicle is programmed to try to finish the job on her own. One of the things that we will get, actually, as part of the communication stream that we're sending back is information about the intense aerodynamic forces and heating that are happening to the vehicle. And that'll be from sensors on the Medley 2 system that Caitlin will talk about next.
Thanks, Al. So I'm happy to be joining you all virtually on behalf of the Medley 2 team to talk about why we're excited to be part of this mission. So as you've heard, landing on Mars is a very difficult thing to do, largely due to the fact that we don't fully understand the harsh entry, descent, and landing, or EDL environment. So the goal of Medley 2 is to collect data to help us better understand that environment, specifically the heating and pressure that Mars 2020 experiences as it passes through the Mars atmosphere. This will also help us to understand what we can expect for future missions. So Medley 2 stands for Mars Entry, Descent, and Landing Instrumentation 2. The 2 is there because it's a follow-on to a set of sensors that flew on the Mars Science Laboratory, which delivered Curiosity to Mars in 2012. Both the Medley and Medley 2 sensor suites were developed through a partnership between NASA Langley, Ames, JPL, and Lockheed Martin Space Systems. And in fact, our centers have been working together for many years on Mars missions, particularly on EDL technology and trajectory development, going all the way back to the Viking days. If you could pull up that first image, please. This shows an overview of our sensor locations. Medley 2 has 28 sensors on the Mars 2020 aeroshell. The aeroshell consists of the heat shield, which is shown in the back of the image, sort of the tan, brown colored item, and that's what faces the atmosphere during entry. And then also the back shell, which is the white PCC up front, and that's what covers Perseverance. Medley 2 has sensors on both the heat shield and the back shell. We have 7 different types of sensors that fall basically into 3 different categories: pressure transducers, which measure pressure, thermocouples, which measure temperature, and heat flux sensors, which measure the heating in the vicinity of the spacecraft. We'll start taking our data a few hours before entry, and we'll continue through parachute deployment. And all of that data will help us to understand several things about the extreme EDL environment. One of those is what's the impact of wind on the vehicle's trajectory. We learned with Medley that MSL's path was affected by winds in the seconds before the parachute deployed, and so we'd like to learn more about that this time around. We'll also learn about the energy and the hot gases that are close to the vehicle. And that heat is really generated in a couple of different ways. One is just from the friction that comes from flying so fast through the atmosphere. And another is radiant heat. So if you think of what it feels like to put your hands in front of a fireplace and you can kind of feel the heat coming off of it, that's the type of heat that we're trying to measure there. And finally, we'll be looking at the performance of the insulation material that protects Perseverance from the extreme heating environment. And the way we do that is to take temperature measurements at different places throughout that material. So what differentiates Medley 2 from the first Medley is that we're going to be collecting better data over more of the entry timeline. We'll do that by spreading out our sensors in more locations, gives us better coverage. And we're also measuring 3 different pressure ranges this time, whereas we only had 1 on Medley. We also have heat flux sensors, which actually touch the atmosphere. So rather than sitting below the surface of the material, these are actually right out there on the surface of the vehicle, touching the atmosphere, and that gives us more accurate measurements. And all of that allows us to seek answers to questions that were raised by Medley and to explore areas that we couldn't address last time. And when we combine the data of Medley 2 with the first Medley, we're going to be able to really improve designs for future entry systems, both for robotic and for human missions. And the way it'll do that is to help us to improve the computer codes we use to predict the environments. Because the Mars atmosphere is so different from Earth's, it's very difficult to test for Mars entry conditions here. And so we rely on computer codes to essentially over-design the vehicle to make sure that we can survive worst-case conditions. But that means the vehicle probably ends up heavier than it needs to be. So if we can understand the heating better, then we can make the heat shield much lighter by up to about 35%. And that'll translate to lower cost, more science, and more supplies for human missions. And then if we can better understand how the vehicle flies, we can have safer and more reliable landings. And that'll help us to reduce the footprint for landing, which means we can put landers closer to interesting science or put people closer to the supplies that we sent to Mars ahead of them. So not only can we extend what we learned to future Mars missions, but like Mars sample return, but we can also extend it to EDL missions at other planets or moons like Venus or Saturn's moon Titan. If you could please pull up the second image. This is an image of a few of our team members after we completed the final Medley 2 end-to-end checkout in late 2019. And this was essentially when all of our hardware was installed on the heat shield, which you see on the right, and then the back shell on the left. So everything was installed and hooked up, and we verified that it worked. So we're all giving the thumbs up because that was a pretty good day for us. And I just want to wrap up by saying that we're very excited for Medley 2 to extend the groundbreaking entry data that was collected by the first Medley. It's going to tell us what Mars 2020 actually experiences during those important few minutes of EDL. And it fills critical gaps in knowledge necessary to advance EDL technology in the future. And in fact, the backshell sensor suite is going to collect NASA's first ever measurements of the heat experienced by the backshell of a Mars entry vehicle. So we're excited about that too. But overall, Medley 2 will give us the most complete data set ever collected from a Mars entry. And with that, I'll hand it over to Jennifer, who will talk about what happens after landing.
Thanks, Caitlin. Well, it turns out after landing, it's not over. In fact, it's just beginning. The science mission is just beginning. I say that, but I definitely know that all of us up here, along with all of you out there, will be breathing a great sigh of relief when we get down safely on the surface. But once we do get down safely on the surface, we're all on the edge of our seats to get those first images from Mars. And so I want to talk a little bit about how we get those first images, when they might come. And then I'll also talk just in general about the things that we do after we land on Mars to get the rover ready for the science mission. So the images. During entry, descent, and landing, at the very end of that UHF pass with MRO we talked about, it's possible that we will get HazCam images. The HazCams are on the front and rear of the rover. That we'll get HazCam images with the lens covers still on in that pass. If we get that, that's golden. Everybody's very excited. We may not get that for the reasons Al talked about. Some of these links drop out. Then we have an opportunity in the later afternoon, about 3.5 hours after landing. There's the Odyssey orbiter flies over, but it's a very low data volume pass, so we will get data on that if things have gone well, but we likely wouldn't necessarily get images. So we have to wait until our 6:30 p.m. pass, which is the Trace Gas Orbiter, a European asset, where we can get a lot more data volume, and hopefully we'll be getting some initial images on that. Those would be the front and rear HazCams with the lens covers deployed, because the rover will have deployed them by then. We potentially would get some of those thumbnail movies for EDL cameras if all has gone well. So we're going to start getting some fantastic imagery and see our new landing site here on Mars from the rover's point of view. Now, the internal checks that we do right after landing are somewhat limited. The rover's had a long day, so mostly just does a few releases of our high gain antenna, those lens covers I talked about, and then we take a nap and we charge the batteries up to get ready for all the things that are happening the next several sols. So if you can go ahead and roll the next video, one of the things that we do across the first few sols on Mars is we know the tilt of the rover, we have IMU data, but we don't actually know the orientation of the rover that accurately. And so what you see here is the remote sensing mast that was folded up on the rover so we could fit in the back shell, has to be deployed. The high gain antenna you can see is over to the right of the image and flat. That needs to be deployed and point at Earth. We actually use the cameras on that remote sensing mast to look around and find the sun. Once we know where the sun is, we're actually able to put that data into the rover's computer, and we have all the other information we need to point that high gain antenna at Earth. And that's what we'll do to command the rover. We send commands through that high gain antenna. So that will happen that first week on Mars. We'll be doing those things. And then we hope to be driving in a few weeks to the helicopter flight demo site. So we'll be looking for a good site, flat site, not many rocks, so we can fly the helicopter. And then after that, we will be driving to our first science sampling site that we hope to get to in the summer or so. So with that, I will say I'm very excited. The team is now shifting their schedules to be on Mars time. Right now on Mars, at our landing site, it's about 2 p.m. local solar. So the team is going to get used to getting up later and then working a little bit into the night. That's not bad to be on a different shift, but the problem with Mars time is that the Mars days are 40 minutes longer than the Earth days, and so you're always shifting by 40 minutes every day, and that gets you jet lagged. But we do this because we want to be very efficient with the mission that we're doing and get the rover unfolded, get the helicopter mission going, and get there getting our first samples. And I have to say, after 5 missions, yesterday somebody asked me, what are you doing to prepare for Mars time? And I thought, I finally have purchased a sleep mask, which I didn't have. Maybe it took me 5 missions to figure this out, but sometimes it's hard, to sleep and everybody's sleeping in the middle of the day. So I'm ready, have my earplugs, and we'll be on Mars time. And to talk more about the science mission, I'll hand this off to Ken Farley.
Thanks, Jennifer. Tomorrow's landing of Perseverance on Mars is the spectacular crux move of this mission. And it really marks a fundamental transition from the getting there phase of the mission to the doing phase, to actually exploring Jezero Crater, as Lori mentioned. There are 450 science team members from around the world, and I will say we are very much ready to take the stage. I want to tell you a little bit about what we have been doing for the last few years and what we will be doing in the next few weeks. The first important thing to understand is that Perseverance is a very capable but a very complicated piece of hardware to operate. And it's autonomous, but we have to tell it everything that it is going to do. We have to tell it where to drive. We have to tell it what observations to make. We have to tell it what samples to collect. And this leads to a daily cycle in which data flows back from the rover to the science team. The science team needs to digest that data, interpret it scientifically, and then together come up with a plan for what we are going to do tomorrow. And then that plan needs to be turned into code and beamed up to the rover to execute. This is a very fast-paced, high-stakes operation. It's kind of a race to get it done. And it also involves literally hundreds of people having to work together seamlessly. And I can tell you, this is not what scientists usually do. Scientists do not usually perform under these kinds of circumstances. And what that means is we have had to train. And so I want to tell you exactly how we went about doing this. We need to get really good at this daily cycle. And if I can have the first video. Here you see an example of one of our training exercises in which we sent a small team of scientists out to the Nevada desert with instruments to simulate what was on the rover. Meanwhile, the rest of the science team, some at JPL and some at their home institutions, did a full-up role-playing exercise for about a week where we went through this daily cycle, and we learned a lot about how this is going to unfold, so we have gotten better at it. And through this kind of exercise and a variety of other kinds of training exercises, we've really sharpened our skills. And one special skill we've had to pay attention to, and it's different than ever before, is the science team is not going to be shoulder to shoulder doing this. For the foreseeable future, we are going to be operating remotely. So literally, the science mission is going to be executed from people's living rooms and bedrooms all around the country and all around the world. It's spectacular that we are able to do that. It's a big challenge, and I think we are ready to do that. Immediately after we land, Jennifer has told you a little bit about what's going to happen. We are going to get some images, and those images will be enormously important for the science team. We have a lot of orbital data, pictures taken from orbiters, but there's nothing like actually seeing images on the ground to get kind of situational awareness. And for a geologist, that is very important. The first few minutes on the field site when you can look around is enormously enlightening. So we'll use that kind of information, the images we get, as well as a little bit of initial exploration to decide what to do. And if I could have the next image. We are very likely to move towards one of several pathways that we have already identified from orbit, one of which you can see here, the green line snaking across the delta. This is a pathway that the science team has identified over the last few years that strings together the key scientific targets that we wish to investigate. These are places where rocks outcrop that we think will tell us the most about the geologic history of Jezero Crater. They are the places where we think there may be evidence for past life on Mars, where we might find biosignatures, and places where we are likely to collect samples. So getting onto that trajectory will be something that we do very early in the mission. So I can tell you that the science team is very excited for this transition, and I personally am extremely excited for those first images that are going to come back. They will be fabulous from a scientific point of view, and also as a huge milestone after so many years of effort in this mission. And now I will turn it back to Marina to handle questions.
Thank you so much, Ken, and thank you so much to all our panelist presenters. We are now ready to take media questions. Remember to press *1 to get put in the queue, and please direct your questions to one of the panelists. We're also taking questions through the Countdown to Mars hashtag. Our first question comes from Chelsea Goad from space.com. Good morning, Chelsea. Chelsea, good morning.
Good morning. Can you hear me?
Yes, we can hear you.
Okay, great. Thank you so much. My question is for Matt. You mentioned the similarities and also the differences between Curiosity and Perseverance. I'm curious, how similar or dissimilar is entry, descent, and landing from what we saw with Curiosity? And what is so different about Perseverance's entry, descent, and landing and what we can expect tomorrow?
Yeah, that's a great question. I'm actually going to go ahead and throw this over to Al Chen. He is our EDL phase lead, and he'll give you a rundown.
Yeah, from the outside, the entry, descent, and landing system looks pretty similar to Curiosity, but there's a lot of under-the-hood smarts, if you will. There are two pieces of new technology that are helping us land at this rugged site. The first is something we call range trigger. That's using the ability of the vehicle to know where it is to deploy the parachute. Previously on Curiosity, we deployed the supersonic parachute just based on hitting a particular velocity. But this time, we're actually asking the vehicle to figure out how far she's flown since entry and deploy the parachute based on that. That reduces the area that we're going to land in, that landing error uncertainty ellipse, quite a bit, almost a factor of 10 in area versus what we had promised for Curiosity. The second major piece of new technology that's helping us land is terrain relative navigation. So whereas on Curiosity, we took pictures after the heat shield came off, but didn't really do anything with them on the fly, they're kind of like tourist pictures in some sense, Perseverance will be taking those pictures and then matching them up with an onboard map based on images from the Mars Reconnaissance Orbiter. It'll use that set of images it's taking and that map to figure out where she is. And based on that, she can then fly to a nearby safe spot once she's done with the parachute and on engines. So that allows us to make sure that to allow a site like Jezero, where the whole landing error ellipse is not a giant flat parking lot. It's full of the stuff that the scientists want to see, but the stuff that I don't want to land on. So that allows us to find little kind of small parking lots amongst those. So those are really pretty key technologies to helping us land. There are also a couple of new systems on board as well to help us understand what it's like to land. The first is that Medley 2 system. That's an upgrade of the Medley system that was on Curiosity. And the second is an EDL camera system that will also have a microphone. So we'll have a lot of new imagery and high-resolution imagery and high frame rate video of what it's like to actually land on Mars. So I'm really excited to hear and see what landing on Mars is really like.
Absolutely.
I'll just add two more comments, which is there's a couple pieces of hardware which we've improved since Curiosity, and I'll just make mention of them. One is the heat shield. We found in our static testing of the heat shield that there were some strength vulnerabilities there, and so we improved not only the design but the manufacturing techniques for that heat shield. The other significant one is the parachute, this big 70-foot supersonic parachute. On one of the technology programs in the Mars program area, we found a potential vulnerability with transient loading as that parachute is inflating and in different configurations. And that led us to conclude that we should strengthen the canopy of the parachute. That's something we did, and not only did we strengthen the canopy, but we took the parachute off and we did supersonic high altitude parachute testing using sounding rockets out of the Wallops facility. It was a major test campaign, something that really hasn't been done in more than 40 years. And the team pulled it off successfully, so a couple more differences there.
Thank you, Al and Matt, and thank you, Chelsea. Our next caller is Irene Klotz from Aviation Week. Good morning, Irene.
Hi there. Thanks so much. My question is for either Matt Wallace or Jennifer Trosper. I appreciate the downplaying expectations with the 50% of Mars missions failed, but NASA has successfully landed 8 of its 9 spacecraft on Mars, including the 4 previous rovers and landers dating back to Viking. So do you have what is the risk of the Perseverance landing overall, and what's the riskiest part of it?
Yeah, it's a good question, and it's a valid observation. I guess I'll say a few things and see if any of the other panelists want to say a few words. We've never really come up with a good way of calculating the probability of success. These systems are so complex, and they're interacting with an undefined environment in many ways that it's very, very hard to give you a number. You know, I think that, but it's those two factors really that lead us to tell you that there's never any guarantees on this process. You know, Mars still has things we don't understand about it. This is still exploration. We're going places that where we're trying to answer questions that we don't have the answers to yet. You know, on Curiosity, and Al can say a word or two about it, we found that the local gravity field at Gale Crater, where we landed, affected our control system. That was a somewhat unexpected thing. You know, it was within the capability of the system to handle it. But those are the types of uncertainties in the environment that we're dealing with. I think you just also have to factor in, again, the complexity of this system. You know, we've got 2 million lines of software code running, hundreds of thousands of electronic parts, you know, miles of copper conductors. We've got more than 70 pyrotechnic devices that all have to fire, closed loop guidance and navigation control systems that really have to operate with sub-second precision for all of this to work. You know, there's no go-backs, there's no retries. It's a difficult and dangerous part of the mission, and I think you have to always respect that as a development team, and I think our team has. So I don't have a specific answer for you on the probability of success. I think we've done everything we can to make it successful. And we'll see how it goes tomorrow. Did you want to add anything, Al? Or?
Yeah, I mean, I guess I'd say that there's nothing like trying to at least use the same kind of landing system again to really find the warts in it. And as Matt mentioned, right, we were able to find a handful of things that didn't go quite the way we expected them to go on Curiosity. And that's humbling, right? I think as soon as if you don't stay humble in this business, and especially going to Mars, you're going to pay for it. So I think it's been key for us to learn from the things we didn't get quite right. But I think, as Matt said, we don't know that we have caught them all yet. We've just done our best to make sure that we've done everything we can think of to make sure that we have a good day tomorrow.
Thanks. Is there one part of the system in particular that gives you greater pause than something else?
Am I supposed to pick a favorite child now?
No, you're supposed to pick your least favorite child.
I think it's hard to point to. I mean, I think that part of it is just the overall complexity, right? Everything that has to happen. Obviously, there's a lot of concentrated risk in that supersonic parachute opening. That it's a very big parachute, right? That's the size of a Little League infield in size. And it snaps open in about 0.6 seconds while going almost Mach 2. So there's a lot of risk concentrated there. But as Matt noted, something we haven't done for 4 decades plus, we actually did high altitude supersonic testing this time as part of this project. So we have perhaps a little bit more confidence that this is going to work.
Thanks very much.
Thank you, Irene, and thank you to Matt and Al. Our third call is from Marcia Dunn with the Associated Press. Good morning, Marcia.
Yes, hello. This question is for Ken. I enjoyed seeing your roadmap with the squiggly line. Is that for all 2 years of operations? And I'm wondering, what's the total mileage you expect to put on the odometer over these 2 years for a nominal mission? And when do you expect to actually drill for the first time to collect a sample in the tubes? When might that be happening? Thank you.
Yeah, the traverse that I showed there is for an extended period of time. We expect that we might traverse up to about 10 miles in the prime mission, the 2 Earth years, 1 Mars year. And we expect that sometime in the summer we'll be ready to take our first sample.
Thank you, Ken, and thank you to Marcia. Our fourth call comes from Amina Khan with the LA Times. Good morning, Amina.
Good morning. Thanks for taking my call. I just had a few questions about firsts, 3, so I'm wondering if you can bear with me here. First one would be, is Perseverance the first machine, I guess, we've designed that could harvest an essential human resource, oxygen, on another world, or has that been done before?
Do you want to take that, Lori?
Yeah, I'll take that. It's a good question. I believe, and hopefully I'm not misspeaking here, that MOXIE is the first experiment that was specifically designed to execute in situ resource utilization, to take advantage of the local environment to transform that material into something that's usable either by astronauts or humans or for other purposes. Of course, we're looking at lots of other types of in situ resource utilization for other destinations such as the moon through Artemis, but we haven't flown those yet. So, but yes, I think MOXIE is the first.
Very cool. Thank you. And is it the first in, I guess, in 45 years since Viking landed to actively search for signs of extraterrestrial microbial life? Or have there been any missions that have done that in the interim?
So Ken, do you want me to take that one, or would you like to take that?
Yeah, you can go ahead, Lori.
Okay. Yes, I would say that Perseverance is the first real astrobiology mission since Viking. Of course, Viking had an intent to look for life, but it wasn't actually, now that we've learned and know so much more, not just about Mars, but about how life forms and how it exists, we know that the experiments that we designed probably weren't quite the right way to go about that exercise. And so we really have followed this more methodical approach this time, first making sure that we had the ingredients present on Mars and that we actually had those habitable environments that were sustained over a long enough period of time at about the right time in Mars's history to really help set us up for success. And so as a result of all of that new knowledge that we've gained over the last couple decades has really helped us to design, as I said, our first mobile astrobiologist that really is, it's one of its main purposes is to seek out those signs of past life on Mars.
Thanks. And when it comes to ingenuity, is it fair to call it basically the sojourner of flying planetary drones? In that, this is basically here to prove that you can fly, and in the future we might expect more flying planetary explorers with more science capabilities on board.
I think you're right on with that comparison. I think Ingenuity is today's Sojourner. When I worked on Sojourner, and there was a lot of uncertainty at the time as to whether or not we'd ever really be able to utilize this technology. And we found very quickly that having a mobile capability on the surface of Mars was incredibly valuable. There's a lot of heterogeneity scientifically on the surface. And just being able to move even a small amount that Sojourner gave us was valuable. And I think in almost every way, when you look at Ingenuity, it looks very much the same. It's a technology demonstration. Its objective is not tied into the science of this mission, but the potential for aerial reconnaissance and exploration in the future using this type of technology is terrific. It's and not just on Mars and other places as well. And so I think it's a great comparison in every way. Looking at the team, they remind me a lot of our team from 20 years ago, to be honest with you. Yeah, so good comparison.
Very cool. And say that you guys don't find any signs of life in the samples using the tools on hand on Mars, and say that years from now, scientists look at the samples sent back successfully to Earth and don't find anything there as well. What could that mean for the future and the direction of space exploration? What does it mean for our search for life on other planets far outside our solar system?
Ken, can you take that?
Sure. I think the important thing to understand about the search that we are about to embark on is that this will be the first time that we have peered in great detail into a past habitable environment, both with the tools on the rover and with the samples when they come back. And we either will find life is there, and that will be a spectacular discovery, or, as you suggest, maybe we won't. But this is a very important observation, because it would suggest that not all habitable environments that exist are inhabited. And I think what that would mean is that we would need to look elsewhere. It isn't going to be a slam dunk. We can't just assume that everywhere that is habitable has had life originate and thrive in it. And I think there are already ideas of other places that can be looked at, both on Mars in the subsurface and as well as other environments, for example, in the moons of the giant planets. So it would be an observation, but I don't think it actually fundamentally changes the direction that astrobiology is pursuing.
Mm. Would it mean the end of Mars exploration in terms of the search for life?
I think that's probably a question for Lori.
Sure. And I'll go out and speculate slightly to say that I don't necessarily think it will be the end of exploration or the end of exploration on Mars and looking for life on Mars. What I think is the most likely outcome would be, if we don't actually get confirmation of past life, would be an inconclusive result, which would mean we still need to keep looking and look harder, maybe in other places. But again, if we are able to even conclusively determine that there's no longer life, there is still incredible science to be done at Mars. Mars has so much to tell us about the early history of the solar system, of the formation of the planets, and of the evolution of the rocky planets. Being able to have Mars in our kind of nursery of planets here in the solar system is a fantastic laboratory to really understand the diversity of planets and the diversity of geologic and climate evolution. So absolutely an incredibly compelling destination for many decades to come.
Thank you so much. I really appreciate it.
Now we're going to head to a couple social media questions. SidXX on Instagram asks, what is the heat shield made of? Caitlin, would you like to take that?
Yeah, so the heat shield and back shell are made of two different types of what we call thermal protection system material. The heat shield is made from PICA, which stands for phenolic impregnated carbon ablator. And I won't go into a whole lot more detail than that, but it's a complex combination of different materials that have, there's a whole lot of work that goes into developing these thermal protection system or TPS materials, a lot of testing, a lot of trying different things to determine what will work. And so PICA is on the heat shield, and then super lightweight ablator or SLA is the back shell.
Thank you, Caitlin. And back to the phone lines. The fifth call is from Jeff Faust of Space News. Good morning, Jeff.
Hi. Quick question for Matt Wallace or Al Chen. You showed the landing ellipse chart. It's in that green box where you want it, although it's near a corner. Have you ruled out any further maneuvers? Are you satisfied with that? What's the last time that you could make a decision in terms of making a maneuver if you needed to for some reason? Thanks.
I can take that one. We do have one other contingency maneuver opportunity late tonight if we decide to use it. However, I think it's very unlikely we're going to do that. The TCM decision criteria here, this bullseye, we're very comfortable pretty much anywhere within that green box, even here on the edge. I mean, really all that this is saying is that we've got a little bit more cross-track error. I think the key thing to remember for our system is that we have guided entry, and we have the ability to correct our trajectory in the atmosphere. So we're just going to take advantage of it. That's all.
Thank you, Jeff, and thanks to Al. Our next call is from Leo Enright from Irish Television. Good morning, Leo.
Thanks, Marina, and good evening from Europe. My question, I'm trying to nail down the hover time that is available to the sky crane. It's going to be placed in an area of 120 football fields of size. If it comes down right at the, if it lands right at the side of that, no need for a lot of fuel. But if it has to go 120 football fields, that's very different. What is the hover time available? And if I may add a supplementary, based on this traverse map we just saw, it looks awfully close to those cliffs. How big are those cliffs, and how close do you imagine you might land to them?
I think I can take those. Good question about the hover. Kind of an interesting misconception about our system is that we actually are never hovering, basically, except for the 1 second where we cut the rover loose. That's the only time the system's hovering. We're on our way down for the whole rest of the time, actually. But I think you're really asking, basically how far can we go and how much additional time that might add if we were to fly further away. We can divert up to about 700 meters in distance from the backshell separation point, roughly. That only adds, because we know we're doing that right away and we're making that correction almost immediately after backshell separation, that only adds a couple of seconds to our flight, basically none at all. If you just sat there trying to hover, our vehicle at touchdown will consume up to about 4 kilograms of fuel per second. So you can kind of understand it that way, we're adding a few more extra seconds of fuel to go the maximum distances. It's on the order of 20 kilos of variation or so. So that's kind of the first question I think you were asking. The second question you were asking, I think, was about the size of the cliffs. Those cliffs are about 200 to 300 feet tall. And you might have noticed that we're aiming right at the edge of that delta. And that's not an accident. The safest place in the ellipse that we would like to come down is at the base of the delta. We call that the landing strip. It's kind of that flat area that you can kind of see in the images. That's at the foot of the delta. So that isn't an accident. If I had my way, we'll end up there. We of course can end up in other places in the ellipse and are happy landing in other small parking lots around the place. But our desire is to end up in that landing strip.
Al, and thank you, Leo. Another call from Ken Kramer from Space Up Close. Good morning, Ken.
Good morning. Thank you. Thanks for taking my question, and good luck tomorrow. My question is for Ken Farley. Actually, I'm interested in the map. If we go back to the map, maybe you could show that map again. Can you talk a little bit more detail about why you selected that route? What rocks and minerals are you expecting to find? And where would you find them? And where would be like the first sampling site that you mentioned in the summer sometime? Thanks.
Yeah. So the traverse that you see there is based on orbital data and the data that we have first and foremost tells us where rock outcrops. And if you want to understand any sort of geologic system, you don't want to analyze, you don't want to study in great detail the rubble that's just laying around. So the first thing we did is identify where there is outcrop. And then we created a geologic map. It tells us how rock units relate to each other. And from that, we were able to raise certain kinds of questions, like, is this rock older than this rock, or is this rock younger than this other rock? And so these become hypotheses that we wish to test at each of these locations. So that's one whole set of criteria for where we're going to go, is where there is outcrop that can tell us something important. And then a whole other set of criteria have to do with the goals of the mission, in particular this seeking biosignatures. So we want a place that is both a record of a past habitable environment. For example, mud deposited in the bottom of a lake. That is a wonderful place to look. So we prioritize targets like that. And also we prioritize targets that could tell us things when samples come back to Earth that we simply cannot answer with the rover. And as an example, we have tentatively identified places where there are volcanic rocks. Volcanic rocks would be spectacular to bring back because then we can date them quantitatively and understand how to pin this entire geologic record into geologic time. So that's how we put the traverse together. It is just an idea, and we are certainly going to divert from it in either large or small ways as we move along and discover new things. And then I think the other question you asked is what would be the most likely first target? That's going to depend a lot on where we land. But if, as Al said, we land right in front of the delta, I would, thumbs up, Al. We are super excited about that because the delta is what brought us to this location in the first place. Spectacular piece of geology. And I think we would very likely look at the base of the delta where there is mud that was deposited billions of years ago. And this is, as I just said, a wonderful place to look for biosignatures. And so I think there's a high probability that that will be, if not the first place, amongst the first places that we will take a sample.
Thank you so much for that, Ken. We unfortunately can't answer all the media questions on air. For those of you with additional questions, please call JPL's Digital News and Media Office. We'll also continue to answer social media questions online. Thank you for your questions, and thank you so much for our panelists joining us today. To celebrate Perseverance's Red Planet landing, cities around the country are lighting the town red. Here's a great look from New York yesterday. The Empire State Building lit up its tower for the Red Planet. Later today, here in Los Angeles, the pylons at LAX will be turning red, and several buildings along the Chicago skyline, including the Adler Planetarium, will also be joining in, so stay tuned today at 12 p.m. Pacific Standard Time as our next briefing will dive into the search for signs of ancient life on Mars and in samples we will be bringing back to Earth. Perseverance is set to land on Mars tomorrow, with commentary beginning at 11:15 a.m. Pacific Standard Time, 2:15 p.m. Eastern Standard Time, and we are offering lots of ways to ride along with us. To join the virtual NASA social and virtual guest events, register for the Mission to Mars Student Challenge and live stream the Mars landing. Visit go.nasa.gov/Mars 2020 Toolkit. For those of you interested in a deeper dive, we have a new press kit available online too, with lots of information and graphics describing the rover and its mission. There you'll also have a chance to sign up and send your name to Mars on NASA's next flight to the Red Planet and put yourself right into the action with our Perseverance photo booth. You can pose next to the rover, place yourself in our mission control, and even see what you might look like taking a selfie on the Red Planet. Again, it's all available at go.nasa.gov/Mars 2020 Toolkit. If you're on social media, join the conversation with the mission on Facebook and Twitter. Follow at NASA Persevere and use the hashtag Countdown to Mars. Thank you again for joining us today and watching, and go Perseverance!